Hey everyone, welcome back to the channel. Today we're diving into power series, what they are, how to find the radius and interval of convergence, and how to differentiate and integrate power series. Let's unlock the full power of power series together. A power series is an infinite series that looks like the following. The summation as n goes to 0 to infinity of c of n times x minus a to the n, where c of n is a coefficient, some number, a is a center of the series, and x is a variable. You can think of a power series as a polynomial with infinitely many terms, and it only behaves well, that is, converges, on a certain interval around a. Our job is to find that interval. In the following example, we're going to find the radius and the interval of convergence for this power series. So, to find the radius of convergence, we use what's called the ratio test. This series converges when it is less than 1. That's from the ratio test. And we write the inequality in the form of the absolute value of x minus c is less than r. Okay, so let's remember the ratio test that we learned earlier. Now we're going to take the limit as n goes to infinity of our power series here by increasing by 1. So that's going to be x minus 2 raised to the n plus 2 power over n plus 1 times 3 to the n plus 1 power. And then we're going to divide by our power series, or multiply by the reciprocal of our power series. Now let's simplify this down. So I can rewrite x minus 1 to the n plus 1 as x minus 2 times x minus 2 to the nth power. And I can also write 3 to the n plus 1 as 3 times 3 to the n. By doing that, it allows us to cancel out some terms in our numerator and denominator. So I can cancel out the x minus 2 to the n power from each numerator and denominator, and 3 to the n from each numerator and denominator. So let's write the simplified form of this limit. So we have limit as n goes to infinity of x minus 2 divided by, times by n divided by 3 times x plus 1. Now the limit as n goes to infinity, we are focusing on the n variables only. So any variable that doesn't involve n, we can factor out as a constant. So those x is treated as a constant. So I can take out the absolute value of x minus 2 over 3, and that leaves us only our n terms inside our limit. So the limit as n goes to infinity as n divided by n plus 3. Now, this is in behavior model where we have bottom equals top with coefficient, and that is 1 in this case. So I take 1 times the absolute value of x minus 2 divided by 3. So that is the inequality I get, or the solution I get from the ratio test. Now remember, this will converge if that is less than 1. So I set that absolute value equal to less than 1. Now we're going to get in the form that we want by multiplying each side by 3. So I get the absolute value of x minus 2 is less than 3. That means 3 is our radius of convergence. You have learned how to find the radius of convergence to a power series. Step 2 to this problem is we're going to find our interval of convergence. And you're going to start by finding the endpoints by solving the absolute value statement that we found in part 1. So remember, that's the absolute value of x minus 2 is less than 3. So an absolute value inequality, you resolve this by saying that's negative 3 is less than x minus 2, which is less than 3. Adding 2 to each side gives the x by itself, which is our goal. And that we see we have the interval from negative 1 is less than x, which is less than 5. Now that is the beginning of our interval of convergence. We know our left endpoint is at negative 1, and we know our right endpoint is at 5. Step 3 is to check each of these endpoints independently and to see if the power series converges at these endpoints. If they converge, we include the endpoints in our interval of convergence. If they don't converge, we don't include the endpoint as part of our interval of convergence. So let's start with the left endpoint of negative 1. So I'm going to take our original power series, which is a summation of n equals 0 to infinity of x minus 2 to the nth power times divided by n times 3 to the n. Now, we know our left endpoint is when x is equal to negative 1. So I'm going to replace the x in that power series with negative 1. And that'll give us the summation as n equals 0 to infinity of -3 raised to the nth power divided by 3 to, n times 3 to the n, which I could take out that oscillating -1 because -3 to the n is the same thing as -1 to the n times 3 to the n. And that divided by still the same denominator. Notice that 3 to the n's now cancel out. And so this power series simplifies down to the summation from -1 to n of divided by n. Now, this is the, we can check and see if this converges by using the alternating series test, since this is an alternating series. Remember, the two conditions for the alternating series is that x of, n plus 1, a sub n plus 1 needs to be less than a sub n, which is true in this one. And the limit is n goes to infinity of a sub n has to be 0, which is true. So I can conclude that this power series converges by the alternating series test. And since that series converges at this left endpoint, so the left endpoint is included in our interval of convergence. And that means I'll include a bracket when I write, with the -1 when I write my interval of convergence. Now we're going to repeat the same process with 5, replacing the x with 5 in our power series, simplifying it down, and seeing what we get. The simplified power series becomes the summation of n equals 0 to infinity of 1 over n. Now you should recognize this as the harmonic series, and we know that the harmonic series diverges. So since it diverges at the right endpoint, the right endpoint is excluded from the interval of convergence, which means I'll write a parentheses when I write my interval with the 5, the right endpoint. Therefore, my interval of convergence for this problem is bracket -1, 5 parentheses. One of the coolest things about power series is that you can differentiate and integrate them term by term, as long as you stay within the interval of convergence. Let's say you're asked to find the derivative with respect to x of the summation of n equals 0 to infinity of a power series, so c sub n times x minus a to the nth power. That is equivalent to the summation as n goes to infinity, n equals 0 to infinity of, now I'm going to take the derivative of my power series. So c sub n is just a constant, and it's raised to the nth power here, so I'm going to move that n to the front and times it by my constant. So I have n times c sub n times by x minus a raised to the n minus 1 power, because remember, I'm just using my power rule for derivatives here. And that's how you differentiate power series. Now we can also integrate power series using our power rule. Doing the same thing here, we can take, this is equal to, the integral of this power series is equal to the summation as n equals 0 to infinity of c sub n divided by n plus 1 power, because my power, remember I divide by 1 more than my power, times my x minus a raised to the n plus 1 power plus a constant c. This is super useful when working with functions that are hard to integrate or differentiate otherwise. Let's look at this following example. Okay, if f of x is equal to the summation of n equals 1 to infinity of x to the n over n, we're going to find the interval of convergence for each of the following. Starting with example A, we're going to find the integral of the summation of n equals 1 to infinity of x to the n over n. Now notice that n is our variable, so I'm going to take the integral of x to the n over n with respect to the n variable, or with respect to the x, respect to x, which is going to give us x to the n plus 1 power divided by n times n plus 1 plus c. Now to find our interval of convergence, we need to start by finding our radius. We find our radius by using our ratio test. Okay, so that's going to be the limit as n goes to infinity. We're going to add 1 to each n here. So that's going to be x to the n plus 2 divided by n plus 1 times n plus 2. times that by the reciprocal of our original function here, which is n over n times n plus 1 over x to the n plus 1 power. Let's simplify this down. So I'm going to rewrite x to the n plus 2 as x times x to the n plus 1. Let's simplify down what's inside our absolute values, and that leaves us with the limit as n goes to infinity of the absolute value of x times n divided by n plus 2. Now to do this limit as n goes to infinity, we can factor out our anything that's not an x, so the absolute value of x can factor out. Anything that's not an n, absolute value of x can factor out. Leaves us with the limit as n goes to infinity of n divided by n plus 2, which is our bottom equals our top for our n behavior model, so that is equal to 1. And 1 times the absolute value of x is absolute value of x. And for the ratio test to converge, that needs to be less than 1. So we have a radius of 1. Now I'm going to take this inequality, the absolute value of x is less than 1, and rewrite it as negative 1 is less than x, which is less than 1. That's our interval of convergence. Well, at least the left endpoint and the right endpoint of our interval of convergence. We just have to figure out, should it include the negative 1 or the positive 1. We do this by testing our endpoints for convergence. So we're going to test the left endpoint. So I go to my integral statement, that highlighted summation that I have up here, and replace the x with negative 1. And that gives us a summation of n equals 1 to infinity of negative 1 raised to the n plus 1 power over n times n plus 1. This is an alternating series, so I'm going to see if I can do the alternating series test to figure out if it converges or not. For the alternating series test to converge, I need to have that my next term, ace of n plus 1, is smaller than my ace of n term. So here's my ace of n plus 1, and I'm going to compare that to my ace of n term. Since my denominator is larger for the ace of n plus 1 term, that means that fraction is smaller, so it does pass that test. Then I take the limit as n goes to infinity of my ace of n, which gives me 0, and so that is also true. So I know that this series converges at negative 1, so I would include that endpoint when writing my interval of convergence. Now let's figure out if it converges at our right endpoint. So I'm going to take my summation of n equals 1 to infinity, replace x with 1 this time, and I get 1 to the n plus 1 times n divided by n times n plus 1, which is simply 1 over n times n plus 1 in our summation. I'm going to simplify this using partial fraction decomposition, and I'm going to rewrite this summation. Okay, I'm going to skip the work of that partial fraction. You can watch another video on how to do partial fraction decomp, but we have the summation of n equals 0 to infinity of 1 over n minus 1 over n plus 1. Now I'm just going to expand out the first two terms so I can see first few terms, seeing what's going on here. When n equals 1, I get 1 minus a half. When n equals 2, I get 1/2 minus 1/3. N equals 3, I get 1/3 minus 1/4, etc. If I rewrote these and regroup my terms, I see I have 1 plus negative 1, negative a half plus a half. That cancels out. Notice all terms after that also cancels out. So I can say that this converges to 1. So therefore, I know my interval of convergence for our integral problem is bracket negative 1 comma 1 bracket. So we're including our two endpoints. Okay, let's find the interval of convergence for the summation of n equals 1 to infinity of x to the n over n. Okay, we're going to start by using the ratio test to find our radius of convergence. So that'll be the limit as n goes to infinity of x to the n plus 1 over n plus 1 times by n over x to the n. Let's simplify this down. I'll rewrite x to the n plus 1 as x times x to the n. Simplify this down by canceling out the x to the n's on the numerator and the denominator. It leaves us with the limit as n goes to infinity of the absolute value of x times n divided by n plus 1, factoring out our terms that don't involve an n. From the limit, we get the absolute value of x is times the limit as n goes to infinity of n over n plus 1. We know that the bottom degree, the degree of our numerator and degree of our denominator are the same. And so that is equal to 1. 1 times the absolute value of x is the absolute value of x. Now the ratio test says it converges when that is less than 1. So our radius is going to be 1. And to find the endpoints of our interval of convergence, I take the absolute value of x is less than 1 and solve that inequality. And I get -1 is less than x, which is less than 1. Now we need to determine if if the series converges at those two endpoints. Starting with our left endpoint, we're going to check and see if it converges at the left endpoint. So I'm going to go back to my summation statement, which is the summation of n equals 1 to infinity of x to the nth power over n, but I'm going to replace the x with -1. So that's going to give me -1 to the n over n. This is the summation of n equals 0 to infinity of -1 to the n times 1 over n. This is the alternating harmonic series. This is a special series that always converges. So now let's check the right endpoint see if it converges or diverges. And I'm going to do that by taking my summation and replacing our x with 1. And that gives us a summation of n equals 1 to infinity of 1 over n, which is a harmonic series, and the harmonic series diverges. So our interval of convergence for f of x is bracket -1, comma, 1 parentheses. For part C, let's find the derivative of f of x, which is the derivative with respect to x of the summation of n equals 1 to infinity of x to the n over n. And so this is equal to the summation of n equals 1 to infinity. And then we'll take the derivative with respect to x of x to the n over n, which is equal to 1 over n times n to the x raised to the n minus 1 power, which simplifies down to just the summation of n equals 1 to infinity of x to the n minus 1 power. Now I need to figure out my radius of convergence by using our ratio test. So it's going to be the limit as n goes to infinity of x to the n divided by x to the n minus 1. Using our exponential rules, that gives us the limit as n goes to infinity of the absolute value of x. And so in order for this to converge, that needs to be less than 1. So we have the absolute value as less than 1, which should be familiar now with a radius of 1. We have an interval with a left endpoint at -1 and a right endpoint at 1. We need to test and see if we include those endpoints or not. So we're going to check the left endpoint first by replacing x with 1. And so in my summation statement, I have the summation as n equals 1 to infinity of 1 to the n minus 1 power, -1 to the n minus 1 power. Let's expand these out so we can see what the terms look like. So that's going to give me, if n is equal to our first term, we're going to get 1 minus 1 plus 1 minus 1. So notice the sum of the series oscillates between 0 and 1 depending on how many terms I'm adding, so this series diverges. And then we're going to plug it in where we plug 1 into our series. And so we're going to have the summation of n equals 1 to infinity of 1 to the n minus 1 power. And that's going to give us 1 plus 1 plus 1 plus 1 plus 1 plus 1, etc. forever and ever. And so that's continuing to grow to our infinity, so this also diverges. So our conclusion is our interval of convergence for our derivative of f of x is parentheses -1, comma, 1 parentheses. You've just unlocked some new tools for approximating and analyzing functions using power series. Let's quickly recap what we've learned today. We defined a power series as the summation of a sub n times x minus a to the nth power. We used the ratio test to find the radius of convergence, And then we tested each of those endpoints for convergences separately. And then we learned how to find the derivative, or we learned to differentiate and integrate power series term by term and then found the interval of convergence with those derivatives and integrals. Thanks for watching. If this video helped clarify power series, give it a like and subscribe for more calculus breakdowns. Drop a comment below if you want practice problems and walkthroughs on Taylor or Maclaurin series, convergence test, or anything else calculus related. Catch you in the next one.